Now let's look at 3 examples which will show how dangerous some gases are when they're mixed with air. If you mix ammonia with air, the lower explosion limit, LEL, starts at about 15 volume%, and the upper limit will be reached at 33.6 volume%. After that, the mixture is too rich to create an explosion, but there is still the risk of a fire hazard. Oxyhydrogen explosions are very dangerous and can occur when hydrogen gas is mixed with air. An extremely wide range of explosion hazards can be found when handling acetylene, which was formerly widely used for welding and in some applications still is used. Practically all mixtures of acetylene with air are explosive. In 2003, a fitter left an acetylene cylinder on the back seat of his van over the weekend. The acetylene cylinder valve was not closed completely and there was a leak. Over the weekend, the acetylene accumulated in the van. On Monday morning, when the fitter opened the van door, there was a huge explosion. The ignition may have been caused by either the internal light circuitry or the automatic door control. Don't let safety be something you learn by accident. As we have seen from the explosion triangle, there can be no explosion without an ignition source. With technical equipment, a large number of ignition sources is possible during normal operation. Hot surfaces are caused by energy losses from systems, equipment, and components. Flames and hot gases can occur inside combustion engines or analytical devices. Mechanically generated sparks are produced, for example, by grinding and cutting machines, and are therefore not permitted in a potentially explosive atmosphere. In general, all electrical apparatus must be regarded as potential ignition sources. With static electricity, the energy stored can be released in the form of sparks and function as an ignition source. Lightning and the impact of lightning can also ignite an explosive atmosphere. Systems, devices, and components which use radiation can be dangerous in the X area. Some examples of these are mobile telephones, photoelectric barriers, and scanners. Finally, adiabatic compression and shock waves inside tube-shaped structures can also become a source of ignition.
If it's not possible to prevent an explosive atmosphere from forming, then it is absolutely essential to avoid these sources of ignition. The most obvious of these is a naked flame, which always possesses enough energy to cause ignition. That is why the use of gas-fueled heaters and smoking are forbidden in explosion protection zones. Mechanical sparks have a similar effect. These can be caused by mechanical machining operations such as grinding or welding. However, sparks are often produced when two metal surfaces simply rub together. In explosive areas, it is therefore necessary to use explosion-proof tools. Mechanical tools must be non-sparking, while measuring devices must be authorized for use in the corresponding areas. Electrical sparks are equally dangerous. These may be caused by electrical operating equipment or when static electricity is discharged. Any electrical operating equipment used in explosion protection zones must therefore also be explosion-proof. The corresponding requirements can be found in the European ATEX 95 directive. Only explosion-proof mobile phones may be taken into explosive areas. Static electricity also builds up when solids or liquids are transported through pipework or during packaging operations. Effective protective measures to prevent static electricity take the form of earthing machines and equipment, and eliminating the use of insulating materials, for example, by using conductive or anti-static tubing, flooring or wheels. Furthermore, flexible parts should be kept as short as possible. Mobile equipment such as trolleys, carts, etc. must be earthed by means of an earth cable and an earth terminal. Hot surfaces of process lines and electrical equipment can be an ignition source. Insulation is not an adequate protective measure. The surface temperature is not allowed to be above the maximum surface temperature. This temperature is connected to the ignition temperature of the used materials.
The data sheets of the equipment must always be studied thoroughly with respect to the gases which may be introduced, and to which additional measures are necessary to create a safe system. As a rule, some equipment, such as gas analyzers, can measure flammable gases and vapors under atmospheric conditions. The sample gas must not be explosive under normal conditions. If the sample gas is explosive in the event of a sample gas supply failure, then only seldom and briefly, in accordance with the Zone 2 definition. All parameters relevant to explosion protection are based on atmospheric conditions. These conditions are absolute pressure 0.8 to 1.1 bar, temperature -20 to +60 degrees Celsius, oxygen content 21 volume%, relative humidity up to saturation. Let's have a closer look at a typical instrument which is to be installed in Hazardous Areas Zone 1. On the side of the gas analyzer housing, you will find a nameplate with all the relevant information about the protection method and the suitable environment. On the top, you will find the company name, followed by the model name or number. Fabrication data, such as order numbers, allow the tracing of the products. Some technical information is given for proper installation and powering. Warnings to the operators to avoid risks during maintenance. Finally, with the X marking, you find details of the design and use of the analyzer in hazardous areas. Let's examine in detail what the X marking tells us. The X symbol is the marking for explosion prevention. Device class 1 or 2, which was described above. Depending on the level of protection, equipment categories are defined for Group 1 or 2. For device class 1, the categories M1 for permanent hazard and M2 for periodic hazard are defined. And for device class 2, 3 device categories are defined according to the ATEX zones. To distinguish the use in gas or dust explosion-proof areas, the equipment is marked with G for gas and D for dust. X stands for explosion-proof apparatus. The ATEX directive marks different ignition protection classes depending on the protection principle. An ignition protection class is a special measure applied to electrical apparatus in order to prevent ignition in ambient explosive atmospheres. Ignition protection classes are divided into electrical and mechanical ignition protection classes. Mechanical ignition protection classes are FR equals vapor restricting enclosure. D equals pressurization enclosure. G equals intrinsic safety. C equals design safety. B equals ignition monitoring. P equals pressurization enclosure. K equals liquid enclosure. Electrical ignition protection classes are O equals oil immersion. P equals pressurization enclosure. Q equals powder enclosure. D equals flame-proof enclosure. M equals encapsulation. E equals enhanced safety. I equals intrinsic safety, IA and IB. N equals ignition protection class for use in Zone 2, non-sparking apparatus. Defines the explosion groups according to lowest ignition current. Explosion groups 1. Methane, coal mining. 2. Explosive atmospheres not in Class 1, 2A, 2B, 2C. These are subclasses for ignition protection D, I, and N. T1 to T6 are the temperature classes in relation to the ambient temperatures. Temperature classes in accordance to IEC 60079-0 are T1 less than 842 degrees Fahrenheit, T2 less than 572 degrees Fahrenheit, T3 less than 392 degrees Fahrenheit, T4 less than 275 degrees Fahrenheit, T5 less than 212 degrees Fahrenheit, T6 less than 185 degrees Fahrenheit, where these are the surface temperatures of the equipment. Toxic sample gas must also be handled with great care. A sample containing toxic gases must not be released into the ambient air. The personnel dealing with it must be informed of the dangers, and the material safety data sheets of the components in question must be accessible. An analytical system handling toxic gas must have a connection for purging the system with inert gas or air. The system must be purged sufficiently in advance of any maintenance, which includes exchanging parts in the sample gas path, such as valves and filter elements. If a toxic sample is fed into a room, the flow must be restricted outside the room and a shut-off valve installed outside the room. An analyzer building must be well ventilated and monitored. Please check local or international safety standards. In biogas plants, we are faced with a combination of risks from hydrogen sulfide, which constitutes a serious toxic hazard. At a level of just 0.02 ppm, we notice the typical smell of rotten eggs. More than 100 ppm of hydrogen sulfide cannot be detected because our sense of smell would be numbed. So we're not able to detect extremely high concentrations, which are life-threatening, in 30 minutes at 500 ppm, or in a few seconds at 5,000 ppm concentration. Methane can also create explosive atmospheres, whereas carbon dioxide and nitrogen are harmful as they are a choking hazard. Every year, people are killed by breathing air which contains too little oxygen. As 78% of the air we breathe is nitrogen, many people assume that nitrogen is not harmful. However, nitrogen is only safe to breathe when mixed with the appropriate amount of oxygen. If the nitrogen concentration is too high and oxygen too low, the body becomes deprived of oxygen and asphyxiation occurs. Nitrogen is widely used as an inert gas, in tanks for example, to prevent the creation of explosive atmospheres. So, if someone says nitrogen, we immediately associate it with safety purging systems inertness. However, we should always be aware that nitrogen can be very deadly. It can act as an asphyxiant and choke a person to death in less than 40 seconds. If a continuous flow of nitrogen is released into air, the oxygen level in the air depletes very fast and can choke a person breathing this nitrogen-rich air. So a worker carrying out a vessel inspection in a petrochemical plant, or even somebody who's merely standing near the open manhole of a vessel being purged with nitrogen, is at risk. Hazard symbols are designed to warn quickly about hazardous materials or locations. The use of hazard symbols is regulated by law and directed by standards organizations. Get to know the hazard identification safety signs. A yellow triangle with a black border incorporating a symbol indicates that there are potential hazards in a designated area. The hazard symbols for chemicals are defined in Directive 67548 EEC. To distinguish the type of hazard, the symbols may also appear with different colors, backgrounds, borders, and supplementary information. What have you learned so far? Industrial environments may have areas of explosion or toxic hazard. You must obtain detailed information from the employer or operator about specific risks at the workplace. Explosions can occur if all three preconditions of the explosion triangle are present. These are 1. Oxygen or air in the atmosphere. 2. There is a flammable substance present, either in the form of a gas, steam, vapor, or dust. And 3. There is an ignition source. Data sheets and warning signs give information about risks under normal operating conditions. The nameplate on installed equipment in X zones gives information about installation requirements and suitability. Read the signs. Don't let safety be something you learn by accident.